And when I say harsh, one is temperature, the other is vacuum. The third one is the radiation from various particles that they encounter. Much of it is known, but there are uncharted part of this environment too. And flawlessly, these spacecrafts have to work here. And coming to the rocket, that's where the rocket science starts. The humankind's ability to access the space is based on the prowess of the rocket that we. And the most difficult part of a journey to space is the initial phase against the gravity and going through the dense atmosphere. 30, 40 kilometers altitude is the most difficult part of any rocket. And if you have to put a spacecraft in any orbit, whether it is 1,000 kilometers or 36,000 kilometers, there is a key terminology. It's a specific energy to put 1 kg into that particular orbit. That is what is to be provided by the propulsion system of the rocket. And that is what is required to be provided by those chemical propellants that we make use of. Recently, you heard about Elon Musk Falcon Heavy flying. It's one of the most powerful rockets of the world of US. There is a space launch system that is being developed. There is an Ariane 6 of Europe, Long March of China, Soyuz rockets of Russia, probably the one which has been flown many, many times, and several rockets of US. Comparably, India has the PSLV, GSLV, and GSLV Mark III. And what is used for the propulsion is either the solid propellants, an oxidizer, and a fuel, essentially, or liquids which are called hypergolic. They come into contact, an oxidizer and a fuel, and then ignition starts. Or the cryogenics, where we use the liquid oxygen, liquid hydrogen, and we have to start the combustion, sustain that combustion. Instead of liquid hydrogen, one can get into kerosene, it becomes semi-cryogenics. The important factor there is the specific impulse what it can deliver for a given mass flow of these propellants. And what is the paraphernalia that we need to carry to ensure the operation of this system? Are you able to hear? So we use a combination of these solid rockets and liquid rockets and cryogenic rocket stages for our launch vehicle. And what we require for that is the propellant, ammonium perchlorate. We use the chemicals, hydroxy terminated polybutadiene, all developed in India by ISRO and the sister organizations. Then we use several materials for our activity. And the touchstone for any material that flies in a rocket, it has to be lightweight. The specific density has to be high. And we have been successful in getting much of this done in India itself. And one of the major contributors for that is our Bidhani, which is in Hyderabad. Then if you look at the structures, again lightweight structures, complex structures, large structures, and when it comes to the mechanisms, if you look at a launch, you will see the spin stages coming down, you will see the payload firing, the heat shield coming out, a great moment for the rocket flight, and once we fail to. And if there is any major deviation in the path of the rocket, you have to destroy that. That also we have seen sometimes. These all have to work with milliseconds time. And those systems have to be foolproof, and this we have today. And when it comes to manufacturing, we deal with difficult metals for working. Precision, even to the level of 1 micron, is important for the components that we work. And if you look at the brain of the system, that is a navigation, guidance, control. If you see a rocket flying, it has to find its position. It has to guide itself to the final orbital slot, that designated place. And when we see after a launch, the result of it, see 35,500 and odd, plus or minus a few kilometers. And that is because of the sensors we use for navigation, the gyros, accelerometers, the guidance systems, and the control that we provide to the rocket. And we do all that very precisely. So when anybody sees the ultimate result of a launch, what we have achieved in terms of those parameters, rocket scientists will know what capability ISRO has in terms of the sensors and the software. When it comes to the spacecraft, the most important part of it is where does it get the power from? And these days we deal with spacecrafts which have about 10 kilowatts power generated in itself, used for the various systems. How do we monitor the health of the spacecraft? That's a telemetry. How do we find the position of it? That is tracking system. And then how do we communicate with it? That's a command system. And what is there sitting in a spacecraft? If it is communication satellite, we have the transponders. And we talk about frequencies which have been designated for that. And what is very important these days is high frequency like KU band, KA band, etc. Imaging systems, we started in IRS-1 with 80 meter, 30 meter spatial resolution, but today we talk about 0.5 meter spatial resolution. That's the kind of objects that we can see from space. And also, in a country like India where we have cloud most of the time, especially when the agriculture activity is going on and the flood is there, we have to penetrate through the cloud, and that is possible if you send energy from the spacecraft and look at the return signal, that is a microwave remote sensing. We do have that capability also. And finally, all these systems coming to the launch pad, you have to assemble a rocket at the launch pad. You can only test it electrically, not mechanically. And then it has to meet all those specifications. And when you assemble a rocket of 40, 50 meters high, there are specifications which have to be met in the assembly, which will ensure that it flies properly. And finally, when you have experiments like space recovery module or the unmanned crew module, that shows the ability for the re-entry. As it enters the dense atmosphere, there are chemical processes taking place which consume heat, which generate heat, and the craft should withstand all that. All this we have done precisely. And when a GSLV Mark III rocket goes up, you will see two solid motors on two sides. They have 200 tons of propellant. Both have to function throughout their flight with identical performance. And if there is any deviation between the two, we are going to get into problem of controlling that rocket. Entire thing is done in ISRO, and we have the ability to predict what will be that performance and control that performance. And that's the capability. And that rocket, S-200 rocket, is one of the 3 largest solid rockets of the world. US, Europe, and then India. They possess this technology. Many times people ask this question, what is the secret behind the cost-effective rocket development in India, or the cost-effective satellite development in India? The key to that is the model principle that we have adopted. The heritage that we have taken from the smaller rockets to the large one. One is the solid system. The second one, if you look at the liquid engine, there is a Vikas liquid engine, which we use in PSLV for the second stage, which we use with some improvements in the GSLV for the 4 strap-ons and the second stage, which we use with extended duration of flight in a twin engine configuration in GSLV Mark III. So we build on the heritage, we take advantage. At the same time, we reduce the development time and thereby the cost of it, and improve the reliability of the system. When we had the GSLV flight in 2014 January successfully, that had the Indian cryogenic engine and stage. And what we have today in GSLV Mark III is a still more powerful version of the cryogenic engine, and that too has performed well. So we are good to stand our own leg on launch vehicle technology and on the spacecraft technology, and that is judged by the import elements, which are limited to a few electronic components or a few materials, and work is going on even to indigenize those systems. And this happens because at the back of our minds this is an obsession, that is self-reliance. What we see on the right extreme is what we did in the Lunar mission Chandrayaan. For India, the objective was to have Chandrayaan mission orbiting moon at about 100 kilometers altitude and to do mapping at 5 meter spatial resolution of moon, which was done for the first time in the world. We also had ability to get the terrain mapping done. We also had the ability to do hyperspectral imaging on that. We did that. We also provided this as a platform for the other nations to put their instruments, and NASA, Europe, etc. And you would have heard the excellent discovery of water molecules which came from one of the NASA instruments put on Chandrayaan-1. That was another part of it. It was an example of how countries can come together and do a mission jointly. And that mission, we had a life of 312 days, but for the first time, we went to a distance of 4 lakh kilometers. Earlier we were talking about Earth-oriented satellites and 36,000 was our limit. Here we went to 4 lakh kilometers. And when we talk about Earth, Moon, we moved out of the sphere of influence of Earth. We had the deep space tracking stations set up in Bailalu near Bangalore to track these ones. And the 32-meter diameter antenna and the control system was done by India. ECL was a major contributor. DRC was with us. Industry was with us. And that's what we developed. And that is our investment for the future in terms of deep space tracking. And there are only 4 such stations in the world today which can get into that kind of deep space tracking. And the next one, we had the Chandrayaan mission. When for moon we talk about 4 lakh kilometers, here we talk about an object or celestial body which is at 55 million kilometers where it is closest, or 400 million kilometers farthest. And if we have to reach that planet, we need to traverse a distance of 660 million kilometers. And if you have to capture the orbit of Mars, And the orbit that we targeted was 500 kilometers and it is closer, and about 80,000 the farthest. We call it periapsis and apoapsis. We had to reach Mars with a precision 500 kilometers plus or minus 50 kilometers after traverse of 660 million kilometers, over 300 days. And as it passed through, there are perturbations coming from Sun and other celestial bodies. And we needed to calculate this 300 days in advance, what is going to be that perturbation over this period of time, and put or direct our spacecraft on December 1, 2003 towards that. We did achieve. And that is the day the international community said, India is at it. So in August 2012, when Honorable Prime Minister declared that India is going to do this mission, where was world with a Curiosity lander in Mars by NASA. And they had done almost 20 missions by then. And for the next orbiter mission, MAVEN, they had gone through their detailed activities and given the final clearance for the assembly of the MAVEN spacecraft to fly. And here India was making an announcement that we are getting into it. So many from this community abroad said, India has an insane schedule. Because we wanted to use the first opportunity, the launch from Earth had to take place in November 2013. That means the spacecraft has to be ready by August 2013, 1 year from the announcement. We had done some homework of 2 years before that. But we were there and we launched it on November 2013, 5th of November. And the rest is history. The spacecraft is still hale and healthy. From 2014 September, it is going around Mars, giving us beautiful data. If you look at the ISRO website, you will know what has come out of the various instruments which are on Mars orbiter mission. But what it has given in terms of technology to us is not only to control such a mission, which is the objective which we have done precisely, ability to communicate with it at this long distance and provide it an autonomy to manage it by itself instead of the ground controllers from Hassan or Bangalore or Bhopal giving it instructions based on its health. We provided the spacecraft ability to monitor its own health and make operations. Because it takes almost 20 minutes at some point of time the signals to reach the spacecraft, and even for us to understand what is wrong there, it will take that kind of a time. And in this 40 minutes plus our thinking time, satellite would have been lost. That is one aspect. There are certain time of the year, especially June, July, there will be no way to communicate with the spacecraft. And for those 2 to 3 weeks time, it has to manage by itself. All these years it has done. Even though we did it at a tight schedule, impossible schedule or insane schedule, as somebody called it, and the spacecraft for the first time, we did it and it is hale and healthy. That means we are not compromised on the requirements of design, testing, quality, etc., for that mission. This is what is unique. And if I use the terminology that people use these days, this has been a disruption in the way people thought about doing an interplanetary mission. That's a lesson for the global community from Mangalyaan mission, apart from the fact that it has given us a technological lead as well as the understanding of the Mars. We will come to the Gaganyaan after some time. People have been asking this question, what is the secret behind ISRO doing all these activities? This is a picture of the control center of ISRO at Bangalore during the time of insertion of the Mangalyaan in the orbit. You look at all those people sitting there. If you see a launch video of ISRO, you will see one of those rooms. There are also several people, almost 500 of them working. That is the last mile of a rocket. It's a job of thousands of people.